You guys just took your quiz on solving by square roots, and we're going to continue with the idea of solving, but learn some other ways to solve. And when I say solve, remember we're finding the x-intercepts or the roots or the zeros, depending on what sort of notation that we're given, whether we're talking about a graph or an equation and we're trying to find the roots, or we're actually subbing in 0 for y to find x, that would be the zeros. But mainly just means let's find x. So the way we're going to learn now is review. We've learned the method that we're going to talk about today, which is finding the roots by factoring. We've learned how to factor. We've learned already when we did graphing how to use the factors to get zeros. So it really is just combining those two skills that we previously learned together. So same section, we're still in section 2.5, which is solving quadratics. But today we're focusing on solving them by factoring instead of by the square root method. Okay. There's just two quick steps to this. Step one, you got to factor the problem. All right, whether that's by guessing and checking or one of our shortcut methods or factoring out a GCF, do whatever you need to do to factor. Step two, you're going to set the factors that have an x in them equal to 0 and solve for x, which we did when we graphed in intercept form. And that's it. After that, you'll get your zeros or your roots. So let's practice some of those. Okay, so I'm just going to write solve here, and we have a total of 5 to do today. After these 5 examples, I am going to pull up a handout, and if you have time during today's lesson, you're going to work on that. Otherwise, it'll technically be part of day 4 lesson, but it'll still be in day 3's video. So example 1, x squared plus 3x minus 18 already said equal to 0 for us. So when factoring, you do have to have it equal to 0. Everything needs to be moved to one side. And that's different than what you just finished with the square root method. In the square root method, your goal was to get x by itself and move everything away from x. We're not doing that here. We want all the terms to be on one side. So it's a trinomial, no GCF, a value of 1, so we can quickly guess and check the factors of c, and because the a value is 1, they'll add to b. So you could have 1 and 18, 2 and 9, 3 and 6. So the pair that can give us a b term of 3 is 3 and 6. To get a positive 3, I need x plus 6 and x minus 3, because 6 minus 3 will give you 3, and 6 times negative 3 is negative 18. You could always remember to check your inner outer. Negative 3x plus 6x is 3x. I'm still going to bring down the equal to 0. Once you've factored it to solve for x, we just set the factors equal to 0 and solve. So the first one, you're going to subtract the 6, and x will equal negative 6. The second one, you're going to add the 3, and x will equal positive 3. And that's it. You're done. Those are your two solutions. Second example, f of x equals 6x squared plus 13x minus 5. Because this is starting off in function notation, when we solve for x, we could refer to those as the zeros of the function. And in for f of x, we are going to sub in 0. It's a trinomial still with no GCF, so we're going to go ahead and guess and check. A little bit more challenging than the last one, though, because the a value is not 1. So we could have 1 and 6 or 2 and 3 for our first two terms. And the last two terms in each factor have to be a 1 and a 5. We're going to set these up. C has less options, so I'm going to go ahead and put the 5 and the 1 in first. And then we're going to play around with whether it's 1 and 6, 6 and 1, 2 and 3, or 3 and 2. signs have to be different because the C is negative. And our goal when we check the inner and outer is to get a 13x. I'm just going to pick a pair. I don't want to put the 6 first because 6 times 1 is 6. And then I get 5 in the middle, and 6 and 5 won't give me 13. Same reason I don't want to put the 1 first and then the 6, because that still won't give me 13 as I'm thinking about it using mental math when I check the outer and inner. I could put the 2 here and the 3 here. 2 times 1 is 2, and 5 times 3 is 15, and that can somehow give me a 13. Let me check to see if those signs work. So I'm actually going to multiply the outer and the inner to verify this. I will get negative 2x plus 15x, which does equal positive 13x. If I got a negative 13x, that would mean just switch your signs. And if you've got a completely different number, that means 2 and 3 don't work. So then maybe try 3 and 2, or then go back to actually trying the 1 and the 6. I'm just going to erase this so I have work to do my zeros. Bring down my 0 equals. Set both factors equal to 0 now that it's factored. And there's a little more work in isolating x because the coefficients are not a 1. I'm going to subtract over the 5 and divide by 2. I'm going to leave my answer in fraction form. So I'll get negative 5 halves. And over here I'm going to add over the 1 and divide by 3. So my other 0 is 1/3. Those are the 2 zeros of the function. You should notice some connection between those zeros and the factors. Notice the denominator of 2 is your coefficient, numerator of 5 is that constant term, and then just like when the coefficient's 1, the signs will be opposite. Works here too, denominator coefficient, numerator constant term, and the signs are opposite. Okay, let's keep practicing factoring. Or technically reviewing factoring since we've already learned this. 2t squared minus 17t plus 45 equals 3t minus 5. This problem has not been set equal to 0 yet, so we need to do that. When factoring, your a value should be positive. So you have to move your terms to whatever side that will keep the a value positive, even if it means moving more things. In this case, we're going to move everything to the left to keep that 2t squared a positive instead of moving everything to the right. So I'm going to subtract the 3t, line it up with your like terms, and add the 5. 2t squared minus 20t plus 50 is going to equal 0. I can go ahead and start guessing and checking, but if you look at this problem, there is a GCF first of 2, so I'm going to factor that out, dividing all of my terms by 2. And then I'm going to factor this trinomial. You could do guessing and checking, or you might recognize that this is one of the shortcuts. It's a perfect square trinomial. 1 is a perfect square, 25 is a perfect square, and if you tested the middle, 1 times 5, that's the square root of each of those, and then you double it, you get the 10. And the signs, when you're checking the perfect square trinomials, don't matter. So these factors are going to be identical, like exactly the same. Square root of t squared is t and t. Square root of 5 is square root of 25 is 5 and 5. Sign of the middle. You could write it like this, or you could write it as t minus 5 raised to the second power. You have 2 of them. When you set your factors equal to 0, they're the same, so you don't have to set both. When you set t minus 5 equal to 0, you're just going to get t equals 5. This is considered a repeated solution. So even though you only got one answer, that answer would count twice. You do not set the GCF of 2 equal to 0 because it does not have an x variable, or in this case a t variable, so it won't impact the solution. it would only impact the y value, not the x value. We got 2 more left. So 81 equals 4x squared. You might be tempted to solve this one using the square root method because you should notice, like a quiz today, that there's no b term present. However, I do want you to practice it by factoring. We're going to move the 81 in order to keep the a value positive. And this is considered a difference of 2 squares. 4 is a perfect square, 81 is a perfect square, it's a difference, so we can do that shortcut method that we had learned prior. Factors are almost identical, and just like a perfect square trinomial, you square root each term. So you can get 2x and 2x, 9 and 9. That's all the way factored. You're going to set your factors equal to 0. And when you get your answer, it's going to be the same number, but just different signs. The first one, you're going to subtract the 9 and divide by 2 to get negative 9 halves. And the second one, you're going to add the 9 over and divide by 2 to get positive 9 halves. You can leave them separate like that, or you could also write it as x equals plus or minus 9 halves, which that is the format you would have written it in if you solved the original problem using the square root method instead of factoring it. And the final factoring example of the day, before we talk about a handout and or start homework, is 10x squared plus 25x. What I would like you guys to make reference in this example is that there is no c term. When there's no c term in the quadratic that's in standard form, factoring will always be the quickest method to solve. You definitely can't do square roots because this is a 25x, that's a b term, so square root method's off the table. But you'll learn another method tomorrow, the quadratic formula, and that would be way too long. Factoring will definitely be quicker every time the c term is missing, because all you have to do is factor out a GCF. So the GCF for both terms will be 5x. I'm going to go ahead and factor out that 5x, divide everything by 5, and factor out an x. And that's done being factored. All you could do is a GCF. We no longer have any quadratics. There's nothing in common. We can't break that apart further. So we're going to take the factors that have the x and set those equal to 0. When you set x equal to 0, that's done. You can't solve anything there. X equals 0 is automatically one solution. The other solution, I'm going to subtract the 5 and divide by 2, and x will equal negative 5 over 2. That is going to be much quicker than the method you'll learn tomorrow called the quadratic formula, which is that long formula you learned in Algebra 1. So it's much better when there's no C term to use the factoring strategy. And that's it on factoring. We just reviewed factoring, which you guys spent 7 days on prior, and then we combine that with our knowledge of setting factors equal to 0 to find the solutions like we did when we graphed. From here, if class is over, you can hit pause. If not, we're going to go ahead and continue on with a handout that'll talk more about what we're going to do tomorrow. Let's find that handout real quick. Sorry, I'm in the wrong screen here. And here we go. So tomorrow is day 4 of this section, the 10-day section total. When we use that quadratic formula that you learned in Algebra 1, the ending is usually where my students get stuck. How to simplify the end of the problem down as far as it goes. So this handout will explain how to do that. So these examples are going to look like what we get after we do that really big long formula tomorrow. And I want to talk about, well, how do I simplify them down? In number 1, I would like to point out that there is no radical and there is no I in number 1. So when there's no radical or I in your answer, what you will do is actually combine these to get a single result by separating the plus or the minus sign. So you're going to do 3 plus 7 and divide that by 2, and then you're going to do 3 minus 7 and divide that by 2 to get the 2 solutions. The top one, when I do 3 plus 7, I'll get 10 over 2, which is 5. And the second one, 3 minus 7, is negative 4 over 2, which is negative 2. Because there was no radical or no I am allowed to combine those numbers together. Now, number 2 has a radical. So when there's a radical present, we can still try to simplify further by looking to see if all the terms have a common factor. That's the only way it can go further. So when I say all the terms, I'm referring to the 6, the 9, and the 12. The 9 is part of the radical 3, so I'm only looking at the coefficient of the radical, not the radical itself. Since it's in a radical, you can't actually do anything with that, since it's already been simplified down. So 6, 9, and 12 are all divisible by 3. So that's what we can do on this problem, divide them all by 3. 6 divided by 3 is 2, plus or minus 9 divided by 3 is 3. The radical 3 stays alone. You can't divide that by 3 because it's under a radical. And the denominator, 12 divided by 3, is 4. Now, even though the 2 and the 4 have a common factor, they don't have the same common factor as a 3 and a 4. So unless they all have something in common, that's it. Okay. We're not going to go ahead and split that up, even though you could do 2 over 4 and then 3 radicals 3 over 4 and separate them, but you can leave them together like this in one big fraction. Number 3 has an I in it. So we also can't go ahead and combine these all together to get a single value. So just like number 2, we're looking at all of our terms for a common factor. In this problem, we can divide them all by 2. So negative 4 divided by 2 is negative 2. 10 divided by 2 is 5, so it's going to become a 5i. And then the 18 divided by 2 is 9. That's all. So you're looking at all the terms for common factors. On number 4, radical again. Look at all your terms. And there is nothing in common. So because there's nothing in common between all 3, this is our answer. You can't simplify this down any further, despite how bad you want to do 10 divided by 2. You can't do 10 divided by 2 because you can't do 5 divided by 2. So they have to go into both. So even though you want to do these, you cannot divide those. 2 has to go into both terms to be able to do your division. Because what I will see every year is this. Students will do 10 divided by 2 to get 5 and just leave the 5 radical 2 alone. That is wrong. They are both being divided by 2, not just one term. On number 5, right now, if you look outside that radical, that would have a coefficient of 1. And 6, 1, and 2 don't have anything in common besides 1, but this problem actually can be taken further. When you get to a radical, you should always check to see if that radical can be simplified like we reviewed. And 20 can. It would break into radical 4 times radical 5 when you find the largest perfect square factor. So you're going to get 6 plus or minus. The square root of 4 becomes 2, and the 5 stays under the radical over 2. Now that you broke apart the radical, if you look at each term, there is something in common between 6, 2, and 2. So we can divide them all by 2. 6 divided by 2 is 3. 2 divided by 2 is 1, which you don't have to write. You don't have to put the 1 in front of the radical 5. And you also don't have to put the 1 in the denominator. 2 divided by 2 is 1, but that is not needed. You can't add the 3 with the radical 5 or subtract them because 1's under a radical and 1 is not. If you wanted to add or subtract them, you'd have to take the square root of 5 on the calculator to change it to a decimal, and then you could add or subtract. Number 6, anytime the denominator is negative, I suggest that when you are looking for your common factor that you divide by a negative number. So looking here, we're going to go ahead and divide them all by -4. So 8, 4, and 4 are all divisible by 4, but because the denominator is negative, not because the numerator is negative, but because the denominator is negative, I'm going to divide them by -4. -8 divided by -4 is +2. When you divide 4 by -4, you technically get -1, but that's a plus or minus 4. When you divide by -4, essentially your plus or minus flips. It would change to a negative over a positive, which is still one positive and one negative. So I know that's confusing, but the sign will still be one positive and one negative when you divide by a negative. And 4 divided by 4 is 1i. You don't have to put the 1. Radical 5 stays alone. And then -4 divided by -4 is +1, and you don't have to write +1 in the denominator. A couple more of these examples. Okay, 2 more. 7 and 8. So 7, that radical 10 can't be broken down. Because there's a radical, I can't combine these, so I look to see if there's anything I can divide them all by. And of course, they can all be divided by 5. The reason why I put this on this handout is a lot of students will just cancel out those 5s and not put a number there, but a number is needed. 5 divided by 5 becomes a 1, plus or minus 1 radical 10. I don't have to write the 1 when it's a coefficient of a term, but if it's a term all by itself, I do have to put the 1. And then a 1 in the denominator, you also don't have to put because division by 1 is just itself. So I don't need the 1 in the denominator, but I do need this 1 because it's a term all on its own. That is necessary. And the last one, the 3 radical is already simplified. You're probably going to want to do 24 divided by 6, which you can't do because if I look in front of this radical, it has a coefficient of 1, and there is nothing that goes into 24, 1, and 6. Therefore, you cannot simplify this. Even though I know you're going to want to do the 24 divided by 6, because 6 does not go into 1, you can't do it unless you really wanted just to divide them separately, in which case you would split the problem up like that. And if you split the problem up, then you could divide to get the -4, and then the radical 3 would still be divided by 6 on its own. But I would prefer if you guys just left it in one big fraction and only do the division and simplification if every single term has something in common. Tomorrow's lesson is going to use this idea when you will use the quadratic formula. The end results are going to look like these expressions, and you'll have to simplify them down as far as they can go. And that is it for today, and we'll learn that formula tomorrow.